Our next section is on physical and chemical properties. So we're going to be able to tell more information about different chemical compositions based on different properties. A physical property is a characteristic of matter that's not associated with a change in its chemical composition. So a physical property are things like density, its color, how hard that it is, melting and boiling points, and electrical conductivity, how much that it can have electricity go through the substance. Those are all physical properties. A physical change is a change in the state or properties of matter without any accompanying change in its chemical composition. So what that means is its chemical formula doesn't get changed. It just changes the state that the matter is in. So candle wax is candles are in a solid state, and when we burn a candle, the wax melts and it goes into a liquid state. But the wax is still wax. In fact, when the candle goes out, then the wax cools and it becomes a solid again. And so it's still candle wax. It's just in a different state. Now we lose some of that candle wax because it goes into a gaseous state from being burned, but still we still consider this a physical change. Uh, Boiling water is another great example of a physical change. The water vapor is changed into liquid water again after it cools. So we boil this and then it goes to the lid. And then when it cools down, then it forms those water droplets that can actually drop back down into the pot. The change of one type of matter into another type of matter or the inability for it to change is called a chemical property. So flammability, how acidic something is or how basic something is, its reactivity level, and something called heat of combustion are all examples of this. We're going to talk about heat of combustion in later lessons as well. So a chemical change would be like rusting of iron. Iron is no longer iron anymore, and it's becoming rusted through a chemical process. Rust can actually eat through iron so that it's no longer useful to us at all. It can completely disintegrate the metals, the metal. So one of the chemical properties of chromium is that it doesn't rust. And this is chromium in picture B here. So we have some other chemical changes examples here. Copper and nitric acid, they undergo a chemical change and they form copper nitrate and this brown gaseous nitrogen dioxide. This is A here. When we light a match, the oxygen in the air undergoes chemical changes to form carbon dioxide and water vapor. Even cooking red meat causes some chemical changes. So the oxidation of the iron in the myoglobin, that's how we get this red meat changing to that brown color. And then in bananas as well, when a banana turns brown, that's a chemical change. We can tell that because the banana doesn't taste as good. All right, so the National Fire Protection Agency, NFPA, they've created what's called a hazard diamond, and it summarizes the major hazards of different chemical substances. So you won't, this is seen in laboratory settings. You might even see this on fire extinguishers or other items that are potentially reactive. More so, you'll probably see these symbols if you end up working in a like a nuclear power plant or some type of facility where engineering is taking place, chemical engineering, things are taking place like that. So these are color coded. Blue means it's a health hazard. Red means fire hazard. Yellow means that it's reactive. And the white means that it's a specific hazard. So um, these blue, red, and yellow, they all have numbers associated with how hazardous that they are. So for a fire hazard, a 0 means that it's not going to burn. A 1 means that it will, but only if it's above 200 degrees Fahrenheit, which is very, very warm. That's warmer than uh, even on a very hot summer day and sitting in your car. That's your car might get to 200 degrees, probably not. So that's a 1 still is a safe level. But then when we get to 3 and a 4, now a 4 says that it could be a fire hazard below 73 degrees Fahrenheit. So that's room temperature. That means that if it's a 4, and this specific example means that it's very dangerous at room temperature. A health hazard, uh, this just means can it make you sick in any way? 4 means deadly. 0 means not. It's not going to be dangerous to you. Reactivity has to do with chemical changes. So something can possibly explode or detonate, or at the very least, if we have a 1, it can be unstable if it's heated up. And then for the specific hazards, this is what is it exactly? Is it radioactive? Is it corrosive? Which means can it burn through things? Is it an acid? Or are we not even allowed to use it with water? And in this case, we can't use it with water. So this has a W and we're crossing that out. Extensive properties and intensive properties. Extensive properties depend on the amount of matter that's there. So those are properties like mass, volume, and heat. And intensive properties, they don't depend on the matter that are present. It's like density and temperature. We've already gone over the periodic table here. All right. Let's go to the next section. There's no practice for this section here. So for measurements, measurements provide the information that is the basis of most hypotheses, theories, and laws in chemistry. Every measurement provides 3 different types of information. A number is the first one. And if we make a measurement with just a number, that's not enough. We have to put the units for measurement. And we also have to talk about how uncertain we are of the measurement. So this has to do with how many decimal places are we going to go to. This has to do with significant figures. And I believe we're going to talk about that in this lesson. If not this lesson, another one close by to this one. So without a unit, a number doesn't mean anything. It just is a number. In chemistry, we used an updated version of the metric system known as the International System of Units, or SI units, and we've been using that since 1964. And so this is worldwide. We use SI units. So for length, we use meters, mass, kilograms. Now, we do use kilograms quite frequently in chemistry, but we can also refer to items as in terms of grams as well. So we're going to look at a lot of units of measurement that say grams per mole. So just be aware of that. When we're dealing with grams and kilograms, you've got to choose one value. Typically, if we have both, we'll change it to kilograms. And then later, if we need to express our answer in grams, we can do that. Time is measured in seconds, temperature in Kelvin. We just add 273 to whatever Celsius that it is, and that's how we find Kelvin. Um, Electric current, we're not going to go over too much in this course. We might possibly, but we read that as the ampere, and that's A. Moles are MOL. And for luminous intensity, that's how bright something is. We call that a candela, and that's CD. These are some prefixes that are good to know, especially nano, micro, milli, centa, and deci. So these might be worth memorizing. If you don't memorize them right away, that's okay, but they will help you with making some conversions and writing your final answer appropriately. Fractional or multiple SI units are named using a prefix. So if we have something that is times 1,000, we say kilo. There's mega, giga, and tera, and you've probably seen these on your computer if you're looking at your computer storage, and this has to do with writing how many bytes that something is, and it's a very common computer language as well. The SI unit for length, again, is the meter, and this is just a brief overview of how we came to decide what a meter was. It was originally intended to be 1/10,000,000th of the distance from the North Pole to the equator. But now we define a meter as the distance that light travels in a vacuum in 1/299,792,458 of a second. So a meter is about 3 inches longer than a yard. So if you're familiar with metric system, great. If you're familiar with the American Standard System, a meter is 3 inches longer than a yard. And these are all relative lengths. So if this was a meter, this is how much an inch is compared to a meter. So a yard's pretty close to a meter here. For mass, the SI unit of mass is kilogram. A kilogram was originally defined as the mass of 1 liter of water. And now we define it by this one specific cylinder of platinum iridium alloy, and we keep that in France. 1 kilogram is about 2.2 pounds. So they say this is what 1 kilogram is, 2.2 pounds, and they made it out of platinum here. Temperatures in Kelvin. We don't use a degree symbol for Kelvin. We do use degrees Celsius for the SI system. It's also allowed. But many of our measurements, we have to use Kelvin for some proportional equations when we're using temperature. So it's a good idea to practice using Kelvin when you can, and then you can express your answer in Celsius if needed. So water freezes at 0 degrees Celsius or 273.15 Kelvin. Now for this class, if you want to round to 273 Kelvin, that's fine. But it's technically 273.15 Kelvin. And water boils at 100 degrees Celsius or 373.15 Kelvin. So we just add 100 to the 273. That's how we get 373.15 Kelvin. Time is seconds are the SI unit of time. Smaller and larger time intervals can be expressed with different prefixes. We can also say hours, days, and years. Volume and density. So the measure of the amount of space that is occupied by an object is the definition of volume. We can use units such as liters and milliliters. And when we express volume, we can cube the dimension. So one decimeter cubed is 1 liter. 1 centimeter cubed is 1 milliliter. Definitely remember this last one. This is used very, very frequently. These are both important, but 1 centimeter cubed is 1 milliliter is very important to know. And we use that a lot in medical settings as well. So this is a diagram showing us what this all means. So here we have this cube, and there's 1 meter going this way, 1 meter going this way, and 1 meter going this way. And so if we find the volume of that, that's 1 times 1 times 1, or 1 meter cubed. And now we have all of these other cubes in here. And so this is what 1 decimeter cubed would be. This would be 1 liter. And then this very small corner of 1 decimeter cubed of 1 liter is 1 milliliter. The formula for density, we're definitely going to use this in class. In this class, and you might need this in other science classes as well. The formula for density is mass divided by volume. The standard SI unit for density is the kilogram per cubic meter. And that's how we read density. But we can also read density in grams per centimeter cubed or grams per liter for gases. So grams per centimeter cubed is for solids and liquids. All right, and here are the associated questions for this section.